And before we go into the science, I wanted to ask you to play a small game, or, well, ask for your thoughts, basically. This is the title of the school, Biological Physics Across Scales, Pattern Formation. And you'll see that it's set up so that it's easy to do this. And start a series of such schools. I think there's a lot to be said about biological physics across scales. And the question I would like to ask to all of you is, what do you think should be the next one? What hot, nice topic that spans biophysics across scales, conceptual preferably, would you also have liked to attend if this had been now? And would you like to attend, maybe, if it were organized in 2 years? That said, let's get back to data-driven pattern formation. And I would like to show you first a few things that I could not show yesterday because of the technical problems. So remember that, okay, so this is, okay, these are just the references. This is the Cindy paper. This is the YouTube channel that I mentioned, that I encourage you to check out. The PIN, the Physics-Informed Neural Networks papers. And now let's get back to the list of models to infer that, that I had presented at first, and that I would like to hopefully go through today. Maybe that's a bit overambitious, but I would like to go as far as I can. But so far, what do you think, which one do you think we can try to infer using the methods that we discussed yesterday, in particular, Cindy? Wait. Okay, it's giving the answer on its own. Great. And thanks for not saying that it's a Lorentz model. Well done. Okay, so this one has very little apparent noise. It looks deterministic. Actually, if you do some statistical tests and look at the distribution of time increments, you will not find Gaussian-like distribution. And so that's a good candidate to try Cindy on it. And so I'm going to take some risks and to try to run it live before you. So this is a small code that I asked ChatGPT to write. Let's be honest. It knows very well how to simulate a Lorentz model, and it also knows how to use Cindy to recover it. So this is the Lorentz model. This is actually what I used to simulate it. Sorry for the spoiler. And so I simulate it. And then I'm going a bit lower down. So I prepare the XYZ data. So we have as input the data and the time. Okay, stop it. And then I define a library of models. So this is here going to be polynomials up to order 5, for instance. That's pretty large and complete basis. Order 5 polynomials in 3D, that's a significant number of terms. I set as optimizer the sequentially thresholded least squares, the simplest one that I described yesterday. I say, okay, fit the data and print the model. And then I will ask to simulate the model that I've learned, show it side by side with the input data. Let's do this. I open a terminal, IPython, and I run. So here's the model that it's learned. It's super fast, as you can see it with a few thousands of points. That was real time, yes. And this is a simulation side by side of the original data and of the simulated Cindy learned model. And while this is a chaotic attractor, so even if it were perfect, you don't expect to do exactly the same because a little bit of initial noise will lead to different trajectories. But that's pretty good. That's pretty nice. So this is an easy model to learn, in a sense, because it's polynomial. The terms are very important in the dynamics, and so it's about the easiest models you can learn. But still, it's nice to see that it works. And it works in a pretty large library, polynomials of order 5 in 3D. That's a lot of terms. I'll stop this. I'll also mention that I did try to get it to run on that kind of data set. So and I could not. So it's supposed to work on PDEs. It's less out of the box, I would say. That time I did not use ChatGPT. And it finds most of the terms, but there's sometimes a little bit something off. And I'm not going to show it live because it takes about 10 minutes to run. Yes?
Excuse me that yesterday I wasn't fully here. So how exactly does the training data look like that you use to teach it?
That's just the trajectory that I showed.
Just that trajectory?
Yes.
And for the PDE?
For the PDE, just the intensity level, so the
raw
data that was plotted.
So you have a matrix with those over time,
yes.
and you
Yes. And I asked it to fit it with a polynomial of order 3 with up to second order derivative terms.
So it can have diffusion.
So it can have diffusion.
But you don't say it has to be.
I don't say it has to be diffusion. Let's get out of the cozy deterministic world and go stochastic now for the rest of these lectures. So all of these other terms, all of these other movies and plots that I showed show, you can even see it visually, a significant amount of noise. And for all of these, we'll need tools that are adapted to stochastic systems. And so what I'm going to do now is to give you a brief intro on stochastic differential equations, and then explain to you how you can fit stochastic differential equations, compare models that you've obtained using these fits, and finally, a bit like Cindy, but for stochastic systems, how you can discover a model using a method that we call parsimonious stochastic inference. And so the first part, so the intro is going to be a classic. The first part of it will be based on this paper, which is the main thing I did during my postdoc. It's a work we started with another postdoc, Anna Frischmann, who's now a professor at Technion in Israel. And it's this paper that we called Learning Force Fields from Stochastic Trajectories. And one reason why I put this screenshot here is because I wanted to show you the painful sequence of dates here. So this was the 4th journal we had sent it to. It was received in February 2019 and finally accepted in January 2020, published 4 months later. Yeah, that was a tough ride. And sometimes it's good to insist. We got rejected in this journal, and we appealed, and we made a case. And then we got very nasty reviews again, and then we made a case again, and then finally the editor was understanding, and he put the paper out. Anyway, enough for the meta-science part. Let's go into the actual math and physics of this. So I've recapped the equation we're going to study today, the stochastic differential equation of Brownian dynamics. First order. And so you have here the force. You have here the diffusion, which is characterized by this Gaussian white noise, and which I've defined using these properties here. And I like to say that to paraphrase someone famous, what I cannot simulate, I do not understand. So how do we simulate this? Well, there's this algorithm called the Euler-Maruyama. algorithm, which is basically the equivalent of Euler integration for stochastic differential equations, where you say that x of t plus delta t at the next time increment equals xt plus f of xt delta t plus square root 2d square root delta t eta t, where the eta t's are independent, identically distributed, and follow a centered normal law. So you just draw these numbers. If you're in D dimension, this is the D-dimensional, of course, and you integrate this, adding these random numbers here. The scaling at square root delta t here is crucial. It means that at short times, the diffusion is dominant, and it's much larger than this deterministic term. But because it averages to 0, because this does not have a mean, the force shapes the trajectory over long times. So today, for the sake of time, I'm going to assume d here is constant, unknown. If it's not constant, you're in the case of multiplicative noise, and you need to be very careful. And in particular, you need to be careful about at what time you evaluate it and how you interpret things. There's a lot of literature here. Don't try to reinvent the wheel. It's dangerous. People say a lot of bad things or wrong things about multiplicative noise equations when they try to simulate them without having looked at what the actual math is. Cautionary tale. For instance, if you start taking x at the initial time point and say, OK, I'm not going to have a force, you're going to have probability gradients that emerge. And you're going to be attracted to the low diffusion regions. While this is not a diffusion-induced effect. This is just because you've done things wrong. Anyway, let's go to the nice world of additive noise, at least. And here we can already see a key element of our inference problem, which is that you can try to read out the force from these time increments, because this has average 0. And to do this a bit more formally mathematically, so if we if we look at delta xt, which I defined as xt plus delta t minus xt, then the average of delta xt over delta t conditioned on the initial point, xt, is the force, f of xt. Why is it important to condition on the initial point? Because this part lives in the future of the initial point, and so it's independent from it. So if you condition on xt, this part will vanish on average. If you condition on the midpoint, you get something else that is not the force, and that is actually 0 at equilibrium. It relates to the out of equilibrium currents. So before, you could use deterministic systems, you could use whatever integration convention you wanted. For stochastic systems, even without multiplicative noise, you need to be very careful. So this is a great equation, but of course you don't get to condition by your data. Typically you have one data point and you never go back to that initial point. So how do we go with learning SDEs? Well, we're going to get back to defining a loss function, defining basis. So we're going to focus on linear combination of basis functions today, just like we did at the end yesterday. You can do nonlinear inference. It's less developed yet, but it's possible. And so with our loss function, Now we have, let's say, as yesterday, we have a lot of possible choices to try to fit delta x over delta t and try to extract f of delta t, f of xt. But there's one that stands out as being particularly relevant, which is this least squares. And the reason for that is that in the case of additive noise, it coincides with maximum likelihood. So to construct this, let me just write the probability of the trajectory x t equals 0 n delta t. The probability of observing this trajectory in a given force field f of x theta. This is a Gaussian integral, because we chose nice Gaussian variables here. And that is proportional. I'm not going to write the normalization constant, because this is a path integral of the discretized path integral. This is proportional to the exponential of -1 over 4d times the sum over t of f of xt, sorry, of delta x over delta t minus f of xt theta squared. This is just a Gaussian integral for the values of these eta t's here. Essentially, you're saying that each of these follows a normal law, a normal distribution, and you factor them in one after the other, and that gives this big product. And now this is nice, because it actually coincides with something we've seen yesterday. We're going to define, so you need to be more careful if you have multiplicative noise again. But this coincides with the loss function we had yesterday. So for the function f of x theta, which is this minus log p, meaning, and yesterday I had divided by the time. I think today I'm going to stick with my notes. So I'm going to divide by 1 over nt, so that this is the average of delta x over delta t times minus f of x t theta squared. There again, this is delta xt, so that xt plus delta t minus xt, and this is xt. And don't move that, because if you do, you don't have independence between the noise part of this, and so that creates biases, and that will change the outcome. But if you don't, if you're nice, then you can just do exactly the same calculation as yesterday. We're going to replace f of x theta by a linear combination of basis function, sum over I of these coefficients times basis function. You can minimizing it, so writing d of dl over dfi equals 0 gives you, it's exactly the same calculation as yesterday, gives you, so you define this matrix B ij, which is the time average of bi of xt, bj of xt, time averaged, and then your inferred force coefficients, fi, is the sum over j of this inverse matrix B, and you take the coefficients ij times the time average of delta x over delta t times bj of xt. And with that, you can reconstruct your force field as f hat of x, so the inferred force field as a sum over I of this f hat I of x. Sorry, f hat I, these are the coefficients, times bi of x. And you can extrapolate, and you can do new simulations with that, and this works. Questions? So that's what we did in this 2020 paper. This version had actually been discovered before and is there in a few textbooks. One thing we did was then to modify it a little bit to make it more robust against measurement noise. And I'm not going to delve too much into the details here, but if you have noise corrupting your data, it's going to get nasty here at this specific point, because you are going to have noise in delta x over delta t, which is amplified by the 1 over delta t, and that correlates with this bj of xt. Here, there's a correlation between the noise on xt here and the noise there. What we found is that you can change the stochastic convention, change a little bit this integral to remove this systematic bias, and at the cost of adding an extra term in the computation. I'm not going to get into these details here because that's not the route I want to follow today. But know that it exists and that you can. This is not robust against measurement noise, but it's quite easy to make it robust. I'll tell you about it. You symmetrize it such that it's, the bias becomes a telescopic sum and cancels out on average. It's a nice result. What I would like to ask you now is, can you trust this result? If I give you a data set, oh no. Yes, if I give you one of these data sets, sorry, it's going to come, and I get the answer here, can you trust this result? Typically, no, right? Typically, you're going to get numbers, but then you want to add confidence on this number. You want to know what the error is. And this is, I think, an important part of this work, which is that we try to evaluate exactly from the data what the error is. So I'll give you the idea of the calculation. And here I want to, thanks Ricardo, to define the error that you're making with your inferred force field f hat as the time averaged mean squared error average over time. And note that I average along the trajectory. So I'm not judging the extrapolation power of the method. I'm trying to know whether along the trajectory, whether along the data, it did well. So that's an important distinction. And it's very hard to do anything systematic about extrapolation power because in the parts of the phase space that you have not explored, you don't know what's going on. So what you can do with just the data is to know how good you're doing along the data. This is, of course, you cannot calculate it because you don't have access to F, but you can try to estimate it. And for this, we're going to write f hat of x equals, sorry, no, let me rephrase this. We're going to write f hat I, the inferred coefficient, as a sum of two parts, fi bar plus zi. This is the best possible fit of your true force field with the data along the trajectory. So this is basically the same b minus 1 ij, sum over j, times bj, f, the true f. And this is the part that comes from the noise. So this is the true force fit. And this is the noise fit, which is the same, sum over j, b minus 1 ij, times, well, times this other part here, or rather in the earlier Maruyama discretization. And so it's b minus 1 ij times the average of bj of xt, eta t, square root 2d over square root delta t. This is the part of the error that comes from fitting the noise. And it's nice because we can evaluate it exactly. This is basically just a Gaussian random variable. Let's do that. Okay, so now if we go back to the true force, relating the inferred force to the true force, we can then write that it's the ground truth plus a remainder that is the systematic deviation due to the fact that your basis may be incomplete, plus this z of xt that you obtain just with this wrong fitting coefficients. So the remainder is the deviation between this f bar and the ground truth. And this part is really hard to estimate just from using a single model, because it's the part that is essentially orthogonal to your model in the true data. And this comes from the noise fitting. So essentially, you have two parts in the error, in the difference between f hat and f. This comes from underfitting. Not having enough functions in your basis. And this one comes from overfitting, having too many of them. And the question is, how do you find the sweet spot between the two? Okay, so let's estimate this overfitting contribution first. Let's assume that R is 0. So I mean, we don't really have to. We can write f minus f hat squared time averaged is z squared plus r squared, basically because they're orthogonal. Because r is orthogonal to all your basis functions. Otherwise, you'd capture some of it. Then this z squared here, that's going to be a slightly nasty calculation, but it should converge in a couple of lines. Z squared of x is, so we had defined z of x as the sum over I of the zi bi of x, of course. Questions before I go deep into this calculation? Yes?
I have a question of something earlier, but maybe I can wait.
Okay. After the calculation then.
Yeah.
Okay, so this z squared of x, we're going to expand this double sum. So that's going to be a sum over I and j of this bi of x, j of x. And then this zi, I'm going to expand them along the sum that's there. Then a sum over k and l of this b minus 1 ik, b minus 1 jl, and we have, okay, this part, the square root 2d over delta t, square root delta t is constant. I'm going to get it out. So that's prefactor here, 2d over delta t. And then we have this time averaged BL eta t, BK eta t. Should be this more or less. And here you see that we have some hope that things will simplify quite a bit. We have BB, BB, B minus 1, B minus 1. Let's hope for the best. This was evaluated over just one time point. So let's do the average. Let's look at the expectation of the time average z squared of xt. I'm not going to write the expectation yet. This time average z squared of the delta t over the trajectory. What depends on x here? Just these two. So if we integrate over x, that gives you the B matrix. So we're going to get 2d over delta t. The average of this gives you, so we have a sum over ajkl. This gives you a bij, b minus 1 ik, b minus 1 jl. And here comes the beautiful thing. This is actually the product of two stochastic integrals. There's an exact relation which is called the Ito isometry, which allows us to compute it exactly. And this is 1 over n, where n is the number of time points, times bl bk. Basically, you have a delta. If you expand over if you expand the double time averaging, there's eta t prime that will come up. So that's a delta t prime on average. And this one will give you directly this. And so that's why you're going to get the same time average. And the 1 over n here comes from the fact that you're summing random variables, essentially. OK, so this is nice, because this all means that we have a 1 over n b k l. Let's collect. What's this? The product of all these matrices. Any idea? B minus 1, B minus 1, traced over the indices such that this one contracts with this, and then with this, and then with this, and then this with this. That's, in the end, a sum over I of delta II, which is just the number of functions in your basis. So if I collect, and I just look at this average squared error here, this average z squared equals 1 over n delta t, so that's 1 over the total time, And on the numerator, you have 2D and B. Now, this is nice because this you can actually evaluate directly from the data. You remember that we've assumed that this D was known. You can also evaluate it quite easily from the data. And so you have an estimate of your error. If you want to be a little more practical even, you're going to ask yourself, what's the relative error? What's the signal-to-noise ratio, or the noise-to-signal ratio that you have in your inference? So let's look at the normalized error. So this delta f squared over f hat squared. So that's this delta f squared. Then this is, and I'm going to write it in a slightly different way. I'm going to write it as 2nb over total time times f hat d minus 1 f hat. This here, I can make an argument, and if you're interested in it, you can look at the PRX paper. This is the information contained in a trajectory about the force field. It's a number of bits, or rather of nats, if we count in natural Bayes. So that's the information So this is the total time times this quantity that we call the capacity. That's the information rate of your system. And the very cool thing that emerges is that this noise-to-signal ratio, so basically the confidence you have that you're not overfitting. I did not say anything about not underfitting, but the confidence you have that you're not overfitting is, as a squared noise-to-signal ratio, the number of fit functions in your basis, so the number of variables you want to learn, divided by the information that you have in your data. Every bit of data allows you to learn an extra parameter with 100% error. Well, that's not great, but if you have now 100 bits of data, or 100 nats, rather, that's without dividing by log 2, with 100 nats of data, now you have a 10% error. 1% over the mean squared, meaning 10% over the values, etc., etc. That's a really nice way, like rule of thumb to decide how many parameters you want in your system, and the trade-off between overfitting and having high error on your parameters you learn, and the trade-off and not having enough parameters. The key thing is that this you can estimate from the data. I'm not using the ground truth. So you can run the inference, also calculate this quantity, and this will actually give you a prediction over the error. Questions? Andrew? Yep. So actually, there's a point at which things get wrong when you're infinite, which is that these matrices stop being invertible.
So it's like an additional source of noise.
Well, it's more like the math doesn't work anymore because you have redundancy in your basis if you have too many basis functions over a finite amount of data. So this is true up to the point where your matrix B is not invertible anymore. But at that stage, this is always going to be 1 anyway. So the noise-to-signal ratio is 1, meaning you're not resolving anything. Yeah. Other questions?
Yeah, your estimate of the force is independent of the noise amplitude, right?
Yes. The error is not, but the estimate is.
Cool. And you mentioned that the diffusion is either known or you can easily estimate it from the data.
In some cases, yes.
I mean, how would you do it?
So if you look at this here, this equation, and if your delta t is sufficiently small, then if you square it, if you square delta x, this part is subdominant, and you get this. So a simple estimator for the diffusion is the average of delta x squared over 2 delta t. There are ways to correct this if you have a bit too long delta t. There are ways of correcting this if you have measurement noise. If you can also fit this time local quantity with a space-dependent basis, and then you'll get an inference of the diffusion coefficient that depends on the state. And actually, to my great despair, this is like most papers who use effectively this method that I'm not involved in, mostly use the algorithm to compute space diffusion coefficient and not force fields. But that's, yeah, it's maybe a marketing problem from my side, because this is called stochastic force inference. Other questions? I mean, you're perfectly right that this is actually a subject. Okay, so let's try it. Taking risks again. Let's try with the Wolf trajectory here. Oh. Second part of this talk. Okay, so I have this package that we call stochastic force inference. There's an old version on GitHub. There's soon going to be the version that I'm presenting now. It's in beta testing. And let's open examples. And oh no, I've given another spoiler, which is that. Okay, so this is what the data looks like. I've just simulated this. I'm going to run the inference on it. So let's do this. IPython terminal. And then I will run this code here, which ChatGPT does not know how to do, and which does, so basically, does anyone know what JAX is? If you're coding in Python, try it. It's, I have to thank João for pointing me towards this, and it's accelerated this code 1,000-fold in a couple of days of work. Yeah, that's worth knowing that it exists. Okay, so I'm loading the data. That's what I'm doing here. Then I can damage it a little bit because I want to test the robustness of the method. Then I call this class stochastic force inference of my formatted data. I compute the diffusion. Then I select a basis, for instance, here, an order 1 polynomial. Sorry, I should turn off this. So the basis I'm going to use is this order 1 polynomial here. And I will ask to infer the force, compute self-consistently the error, and print a report about what it's done. And then a bit after, I'm going to provide it the exact model and the exact data, and ask it to compare. And finally, I will ask it to do a simulation of the learned model and compare it with the true model. And contrarily, of course, to the Lorentz model, they're going to immediately diverge, right? Because this is a stochastic noise-driven system. So there's not even a Lyapunov exponent. It immediately gets in different direction. Let me run this. Okay, 100 data points. And that's the trajectory on top. On top. No, come on. And here, so here we're seeing the trajectory, the input trajectory. Not so great, right, the data. And just with the data, I've estimated that, well, I had 159 bits of information. That's not so bad, because remember that that's the denominator here, so that allows me to learn quite a significant number of parameters. And so self-consistently, I estimate that I have about 7% noise to signal ratio. The actual deviation is a factor 2 over, is twice as much. But this is, of course, an estimate, right? That's stochasticity. From one realization to the next, it will vary. I can also infer pretty well the diffusion with a few % error. And here what you're seeing is I plotted along the trajectory the true force in X and the inferred force in Y. And you see that basically it's this nice cloud of points with relatively controlled. So what we can do is self-consistently say what the spread of this would be. If I add a lot more data now, so I'm going to, yes?
In the report seems to be quite good, but I don't know if it's my eye, but the slope, it's...
Sure. There's a bias, because this is on one single data set. I've learned a single model. And so there are systematic biases in this single. I mean, on average, this bias is 0. But for a given, for that 100 points, that's what I get.
But it's not systematically biased.
It's not systematically biased. And let me show you by showing the same thing with a longer trajectory. So now I have 5,000 points. And now, well, it's still a bit tilted in a controlled way, but much less so than before. And so if I have even more data, it will align more and more. That was example 1 of these systems. There's another one that I want to go through quickly now, which is that these self-aligning, self-propelled particles. So now this is actually a much harder problem. I have, I don't know, 36 particles, I think. Each of them is described by 3 degrees of freedom, its position, x and y, and its angle that I assume I can observe. And so this would, if I try to fit this with a 36-dimensional polynomial, this would be awful. This would not work at all, right? I would overfit immediately. But what I can do is use the symmetries of the problem. I can say, OK, I don't actually care about distinguishing particles from one another. I don't actually care about distinguishing space direction from one another. Let me just write the force on particle I as an external force of xi plus a sum over j of pair interactions and expand these onto basis functions. The key point here is that the index xi, the index I is only here, but it's not in the forces. I'm trying to learn the same force, the same interaction for all pairs of particles. And that will improve a lot actually, if you do that, the more data you have, the easier it is. So this one, I'm just going to take a polynomial. And this one, let's say that I'm going to put 2 different physical ingredients. I want some radial forces. So I'm going to say that there's a function of a sum over I over alpha, let's say, of B alpha of Rij times Rij. So this is central forces. And I also want some angle-dependent interactions because, well, it looked like they were aligning when you run the simulation. So maybe let's put that. And anyway, if it's not there, the coefficients will be set close to 0 and will not matter much. And so I'm going to have also a sum of B prime beta of Rij times was it a cos? Sine theta I minus theta j. And that's going to act on the theta part. I'm a bit squeezed for time, so I'm not going to go too much into these details, but let's see how it works in practice. Okay, so I'm going to quit this and another example of active Brillouin particles.
That's
So
a minimum sort of idea of how a particle moves, right? You're already thinking about that.
I'm modeling here. I'm proposing hypotheses, and I'm not retesting them yet. So here's how they move. That's the data set. Quite a big data set, actually. It's a CSV file that's 15 megabytes. And now, if I run again the stochastic inference, so same as before, I load the data, I compute the diffusion, and now I'm going to decompose these. I'm going to use Gaussian kernels centered at different radii that I've defined depending on the histogram of distances between them. And I'm going to say, OK, I want to fit with self-propelled particles with angular and radial kernels on a polynomial fit. Infer, and as before, compute the error, print the report, and compare to the exact results. Let's do this. Loading. 300,000 points. OK, that's a decently sized data set. I mean, it's a few minutes. I mean, it's like 1 minute of a movie with 36 particles. It's not really crazy. At least in soft matter, it's very reasonable. OK, it's done. And now it's finding a mean squared error on force and diffusion that are about 0.4%. Wow. That's the output plots. So, OK, this is just the trajectories. This is this exact same thing as before, but so force as a function of, like exact as a function of inferred for all components over the whole trajectory. And you see that, well, it's doing really well. Even more important, I think, is the fact that if you look at the angular torque and the radial force, this is the exact in orange and the inferred one in blue. And in the gray region, that's when particles are too close and they repel and there's no data. So you should not look at this part. So in the part which is sampled, you're getting really, really close. And that was with 300,000 points. But actually, if we do a much, much smaller inference, so I have a tiny data set that I can even downsample a little. Oop, should go faster. 7,000 points. Okay, that's not so little, but it still works really well. You're a little bit off now with the angular force because it's not so large, but you can still make use of this with a few thousands of data points. And this is, so this number of data points is the number of particles times the number of time points, right? It's not the total number of frames. OK, so it looks like it works. I'm happy to share the package with you if you would like to have fun with it. And now we've crossed 2 more models off the list. I would like to go through a slightly more new part of this project and tell you about now the work of my PhD student, Andronis Gerardos, who's about to defend his PhD in a few months. and about to submit his main PhD paper in a few, weeks, probably not days. So I'm going to tell you about the method that he's been developing to compare and select models of stochastic differential equations. And because, well, it's nice to have an audience, I would like, please, to that each of you acts as a referee for this future paper and give me a referee report at the end. Just kidding. But feedback would be very welcome because this is not engraved in stone yet. Okay, so the question now is, how do you compare different models? Where's my... So imagine that we have two bases now, B and C. And we want to know which one is the best, which one provides the best fit. The tempting idea would be to look at the loss function, right? The loss function is what we've minimized to find the best model. So the lowest one should correspond to the best model. So if we look then at the evaluation of our loss function, so that's the loss function of how should I write it? Of our trajectory, so the set of xt and the inferred force. I'm now going to add a small index here to say which force field I'm considering, because I'm considering different. So this is the outcome of stochastic force inference for basis B. And how do I compare this? And I can compare this with the outcome of stochastic force inference for basis C. There's a major problem here, and that will make it prevent it from working, which is that we've used this trajectory, our xt, both to compute the force coefficients and to evaluate our loss. And there's correlations between the two. And these correlations will make it so that the larger the model you use, the better it will fit the data that you've trained it on, right? That's why you typically split your data into training and testing sets. So we have two routes here. One route is we can split the data set. And it turns out that this is not so great, actually, because you're throwing away a large fraction of your data that could have been used to improve your inference. And there are problems in the validation too, which make it so that actually this does not work great. At least we haven't managed to make it work great. What we've found, however, is that the other possibility is to remove the bias.
Yeah, and this doesn't come back in your overfitting when you determine your overfitting, as you just showed.
It does. It does. We're talking about overfitting here. But
you said also that you also were just saying that if you look at your loss and you minimize it, you will be selecting a model which is more complex because it will be doing better because of this. Because of this correlation. Because you trained it on the data set and you're looking at the data set. But wouldn't that be, yeah.
If I use this as a score to compare models, it will prefer more complex models. Now
So intrinsically you don't get away with that, okay?
Yes, I mean, all I've done before was for a fixed basis. So there was no question of comparing, right? Yeah. Now I'm comparing and I'm saying, okay, this thing here is not the right quantity to look at if you want to compare models, because it's biased. Yeah. But just as before with the estimation of the error, we can work out the value of this bias. And I'm going to to split a few, to skip a few steps here and say that actually so the error, so this is a computation that Andonis made. The expectation of the loss of x given fb minus the loss of x given the null model. The null model has just zero force. It's just pure diffusion. This one we can work out exactly. So we cannot get the loss of, yes, no. We can work this out exactly. And this is actually, with some small approximations here that I don't really want to discuss, but it's not completely exact, equal to the total time. No, there's no total time because I've divided by time in the loss too. So this is equal to the expectation source value of the difference of errors that you're making. So you remember the error that I had here, minus the error of the null model. The null model has an error too, right? It's just the average of the true force squared. So that would be great, but this is not actually complete because there's plus the number of functions in your basis divided by the total time. This says that actually this L here, the difference so this is actually a very important result. The difference in loss functions relates directly to the difference of errors, but there's a bias here, which is this NB over T. So if I cast this again as a difference of log likelihood, so L, remember I had divided by the total time, yes. So now I'm going to define a quantity that debiases it, right? If now I look at this quantity that I will call I, that is the total time times L of x fb, so that's going to be my IB here, minus L of x given the null model, minus NB, minus the number of functions in your basis, then this guy is actually an unbiased way of making a good, how to say it? It's an estimator of this difference of error, and so it's a fair way to compare models. If you have two models, the data tells you that you should choose one that has the highest IB, lowest, highest.
Is this?
Lowest. This has a name.
Is this Ikeika?
This is Ikeika's information criterion that Veronica told us about last week.
It felt familiar, but I've never seen it like this. It's very nice. Very nice.
This is
Wow.
AIC, reinvented by my PhD student who did not know about it, and I didn't know about it either. So
very elegant.
it's this way we feel like we own it. You know, when you really understand how wheel works once you've reinvented it once or twice. So this one wheel we've reinvented. Of course, we could have saved a year of PhD. Maybe not so much, but we could have saved a few months if we had known about it in advance. But then it wouldn't have been as fun, and we wouldn't have understood what's next. This is a great way to compare two models. However, And yes, I can show you how it works. And for instance, oh no, my battery is dying. Yes. So for instance, if you look at the difference of information between two models, a simple one and a more complex one that has a better fit power, as a function of the total time, what you'll get is that this difference of information will cross over. At short times, you'd say, okay, I have very little data, I don't want to overfit, so let's choose the simple model. Yeah. At large times, I say, okay, it's going to say, okay, now actually, I have a pretty good confidence on the fact that the more complete model, even though it has more parameters, is providing a better fit. And so it crosses over this way. And if we look at the actual error that you're making, the crossover is at the same time in the true error. So the top line here is what you as operator, given a data set, can look at. The bottom line is the omniscient simulator that knows what the true model is. But you don't need to look at the bottom line. You need to look at the bottom line to know what the absolute error is. But the comparison between the two, you don't need it. To know which one does better, you can just look at the top line. Mm-hmm. And so that's a way to decide which one of two models fits best, whether it's there's a complexity trade-off. The more terms you add, the higher the complexity. So the higher this penalty in the criterion, but the better your fit. This tells you where you are in this trade-off. And so that works nice. And now, last part. So this was comparing two models. Last part is discovering models. One among many. So we know how to compare two models. What's tempting to do? We're going to have now, just as with Cindy yesterday, we're going to start with a large basis, B0, that can be, for instance, polynomials, sines, exp, other terms, wavelets, radial kernels for the terms that depend on the alignment on the, or if you're in a multi-particle system, terms that depend on that include alignment, that include vision, maybe cone of vision of your particles to include non-reciprocal interactions, etc., etc. You can put all this in your basis and then try to find what's useful in it. Okay? So now you'll find for any B that's included in your B0, you can compute your IB. And let's do this. And we can order them according to their complexity. So as a function of NB, and for today, I'm going to assume that somewhere there's a true model with no remainder. And maybe we'll say that it's here. And that's the information. Okay, so if you're at the null model, what's the information of the null model without any parameter? The null model has 0 parameter and 0 here, so it's 0. Good. Then we're going to start adding parameters, and we're going to start capturing something. maybe I should not go that high. And that's the information of the complete model. Here you have, and of course you have below many terms, many models that don't have the right terms, that have other terms that fit less well the data. This is the one you want to get. And all the next ones actually have superfluous parameters. There's, I'm adding a useless part, and because of that, it's penalized. The AIC will tells you that this difference of information relates to the difference in error, and the error is going. The error is going to increase because you're going to fit more and more the noise, and you don't add anything useful because you've already have the full fitting power of the data. So what you expect is that this should go down. What you see is that actually what's going on is that you observe a bump, and then it goes down. And that's bad, because if you use this criterion to try to select your model, if you try to maximize this I, what you're going to take is this guy. Why? Because there are many models here. Each of them individually is below. But if you look at the max of a large number of random variables whose average is negative, the max may be positive. And so what Andreas has done, and I'm going, because I have just 15 more minutes and I want to show you some of his results, I'm going to skip the calculations. What Andreas has done is worked out the extreme value statistics of this distribution here to try to understand, okay, the thing is I have a large number, if my basis is large, I have a large number of candidates, each of them is penalized. What's the law of the maximum? What's the law of this term here? And the law of this term is actually given by the maximum over all the superfluous terms, so all of these terms that you can add here, that I will call S1, Sn, and B0. Sorry, so the maximum over I of the delta I between, so this delta I is the I of B star, let me call it B star, the true model. Of B star minus I, B star plus a useless term Si minus I of B star. If you assume that Si is superfluous, meaning if you
What was SI again? It's all of those?
Si is one of the basis terms that is useless.
Okay.
It's a superfluous term. If you assume that it's superfluous here, this here is a random variable that follows a chi-squared law, and I'm going to say it a bit loosely. It's essentially a Gaussian random variable, eta squared minus a bias. I think 1/2. don't take it too literally. You can work this out. The maximum over n variables of the maximum of n random variables is an interesting mathematical problem, an extreme value statistics problem that you can, in a physicsy way, solve by saying, okay, let me look at my cumulative distribution function of the random variable. I'm going to split it into n quantiles. And I'm interested in the midpoint of the last one. So I have n here, and this is the midpoint of the last one. And this is a good estimate of the typical value of the largest of your n random variables. Now, for this type of random variables, this is approximately log n, log of the total number of variables. If you had Gaussian random variables, you'd have square root log n. But here we have squared Gaussian random variables, so this is proportional to log n. Question? Okay, so now what Andonis proposed is to modify your criterion, modify this information here, to penalize such that this term becomes tilted and we put it down. Not only that, because actually if we make it flat, fluctuations at this level will still prevent you from doing the inference. From time to time it will work, from time to time it will not. And so on top of that, he adds a confidence interval that he works out using the standard deviation of the maximum and using a 3 sigma rule, saying, okay, I want to have 3 sigma certainty that the next term is not a wrong term. What this gives is a modified criterion that we for now called the GIC, Gerardo's information criterion, which is the previous one that we had before, IB, minus, sorry, let me get the exact formula that he sent me this morning. This is very fresh. I mean, we've been working on this for 3 years, but it's converging. So let me rewrite it from so minus the total time times the log, the loss function that we had defined there, minus total times time L, plus K, plus NB, plus NB times, so that's the AIC penalty, the usual one. And then there's an extra penalty due to this extreme value statistics and the confidence interval, plus NB times log of the total number of NB0, the total size of the basis, plus 3 times the standard deviation, and the standard deviation is 1/2 of square root 2 pi squared over 3. There. If you do that, and if you penalize all the models according to this, you're actually looking for a model. The maximum of this quantity is a model for which you have 3 sigma certainty that the next one is that with 3 sigma certainty, the next one isn't a useful model. So or rather okay, I'm getting a bit confused. Let me show you how it works. So now what Andonis does is a 2-step algorithm that we call parsimonious stochastic inference.
What is the pi?
Gaussians, pi,
Oh,
pi, Gaussians. Yes, that's
because of that distribution.
that's because of that distribution. That's a Gumbel distribution, standard deviation. Yeah. That we call pastis. And the idea is, one, we find the best model, the one that minimizes the loss, for each value of k. So we explore submodels of B0 using an algorithm that we call single best replacement, that is called single best replacement. So typically, this is not doable exactly because this is an NP-hard problem. There's 2 to the NB submodels. But if you do a random walk along these submodels, allowing for substitutions, removal, addition, you're actually pretty efficiently exploring it because it's a relatively structured space. So single best replacement. That allows us to construct this maximum as a function of k. And then, among them, the top ones, select the one that maximizes geek. And this is, I think, a quite principled way of selecting models, which accounts for several things. It accounts for overfitting, and it accounts for multiple hypothesis testing, meaning accounting for the fact that the larger the basis you have, the more likely it is that you have a false positive. And so that's where this log of the basis comes into. And it accounts for statistical significance of the difference between these, which is this term here. If you sum it all and try to apply it, and then I'm going to show you some of the results of that Andonis has been working on. So, for instance, if you look at the population dynamics data set, the many trajectories that we had before, that we have simulated using this Lotka-Volterra population dynamics model. And you see these nice patterns in the talk. So that's governed by dx over dt equals reproduction, interspecies interaction, and competition. And here I've added environmental noise. So that's not the demographic noise that Nigel used. It's proportional to x and not to the square root of x. But this doesn't change much. This is the input data. And if you use this input data to select a model using pastis, what you'll find is this interaction network. This is a sparse interaction network. We have 7 species, so 2 to the 7 squared plus 7 parameters. That's about 10 to the 17 models. And we're trying to find one out of them. And we haven't found it here. There's a few false positives in orange and a few false negatives in gray. Now, if we have a bit more data, then you find it exactly. You pinpoint the right model in 10 to the 17 models.
And if you had just used the ICTP?
Then you'd be completely wrong. You'd have many false positives.
Can I be a referee? It would be really nice to see that, how pastis is getting it. Just to have intuition, right? You see?
Where is it? Yes, this is AIC. This is Cindy that we tried on these two, and pastis is converging to the ground truth. Now it's going to be time to conclude. I want to show one more thing, one more of the data sets, which was the field. So far, in our basis, we only had scalar functions, and our data set was just a vector. But you can also add to the basis operators. And such, and try to construct your SPD with that, a stochastic partial differential equation. That's what Andonis did with this video in a quite brutal way, meaning that he put all terms up to fourth order polynomials and up to fourth order or up to second order derivatives with all the cross terms, the advection terms, the du, dx, dv, dx, etc., etc. There's 80 different possible terms in this basis. So 2 to the 80 possible models to explore. 2 to the 80 is 10 to the 24. And with just one frame, so that's with the first frame, we have so far the null model for V, 0 plus noise. Actually, it's picked up a grad squared for U already. Now let me add some data, and as the movie runs, we're going to run past this over the whole data set up until that point. So add a little bit of data. Oh, new terms have appeared. The gradient has been, the Laplacian has been picked here. And then if I keep adding data, new terms will appear one after the other. And you may recognize this type of model. It's actually a Gray-Scott model with stochasticity. And that's emerging out of the 10 to the 25 different possibilities without a single wrong term. I have to say I'm quite happy about this. And I think this is a promising way in the future to explore dynamical pattern-forming systems from data. So far, you can see that the frame count is very large, a few hundreds, even though you haven't seen much. So you need really high time resolution, or you get a few terms that are wrong. That's something we hope to improve. We also hope to make this more resistant to ambient noise, but it's already working relatively well. And then we want to apply it to data. I'm going to conclude here. I'm going to flash the fact that, okay, this last data set that I haven't discussed, no, there are actually 2 data sets I haven't discussed. This one was underdamped and had inertia, and you could see it by the fact that it has all of your birds, quote unquote, have a well-defined velocity. And if you want to apply inference methods to that, and if it's stochastic, you need to be careful. The math is actually much more complicated than what I did before, because there are correlations between estimated velocities and estimated accelerations that generates biases that you need to correct for. If I flash the math, you'll understand why I did not do this on the blackboard. It's not that often that you have a 6/11 prefactor in a complicated matrix that enters there. But at the end of the day, we managed to get this to work. And from this green data set, we can infer a model that looks like this red data set that has the same dynamical statistics and the same similar properties. This is nice. This, however, requires really nice data. And for instance, we haven't been able to apply this to bird flocking for simple reasons, which is that birds flap. And so over the time scale of a flap, you're actually not stochastic at all, so you need to filter this out. And if you remove that and look at larger time scales, then the inference breaks down and you're not able to infer. And so there's some work, some progress needed in order to make this more robust and allow us to do the inference in that kind of cases too. I'm going to go very quickly. These are applications that we've done, allowing to do inference of models over single cell dynamics. This is an epithelial cell crawling in a micropatterned patch. We can do this with many of them and try to infer models, and this was the work. I mean, the The underdone part was the work of David Bruckner, who's now not in Vienna, but in Basel, actually. And yes, this was one of several possible applications. This actually led to really nice inference of models that are really different for cancer cells and for healthy cells. The healthy cells repel each other and stay in place and have normal friction. The nasty cancer cells actually have attraction towards each other and negative friction that allows them to slip and accelerate by each other. And you can just imagine how bad that can be. This is a snapshot of a small part of some of the users of the methods. And well, I hope this will keep growing. And with that, I would like to thank all of you for your attention, and I hope that we have many questions at the end. I want to thank my group members, Andonis in particular, who did this last part of the work, João, who is the one who's working on the last data set that I have not shown, and you're welcome to ask him what this was and how he solves it. My collaborators, Anna, David, and Chase on these works. And I want finally to say that we have PhD and postdoc positions available in the campus of Marseille, in Lumini in Marseille. And if, I'm sorry, Ricardo, I had to do this because of you. If you want to know where this is here. That's the campus. This is the city of Marseille. It's a nice, beautiful, messy city. If you like it here, you like it there. And if you take a short walk, about half an hour, and you go all the way here, you can take that kind of pictures. Thanks for your attention.
Spaniard, I have to say, the only problem is it's in France. Questions? Well, thank you, Pierre, for the great talk. Questions?
So my question is, when you were showing how well it works, the pastis, I was very impressed, by the way. But I was just wondering, if we do apply this to data, right, for which we don't know what the model is, right? Yeah. And given also, so in this case, you know the equations that have generated the data, you can put noise on top of it, and then you can say, okay, how well were we to the ground truth, yeah? But because you're modeling a PDE onto a PDE, something generated by a PDE, or ODE onto something which was generated by ODE, you somehow, it feels to me, that there is a little bit of this cheating there, because we're not cheating, but we're not on the same level of the phenomena. So I don't even know if a pattern I see is describable by a PDE. And so although I might say, okay, fitted to a PDE, right? What about that fact that there might be these underlying levels, right? We were talking about multi-level modeling of pattern formation. Do you think this could introduce some issues to, by the way, and it's not that I'm criticizing pastis, this would be to any of these, but at least, yeah. So what is your opinion about this, or have you thought about it?
It's a great set of questions, I would say, and we're thinking about all of this a lot. First, what I've shown here and the proofs I show assume that the class of models that you're considering is right. That's never the case. Any experimental data cannot be, does not obey a well-defined mathematical equation. All the models are wrong. They may be more or less wrong, but we're trying to aim for the less wrong ones as much as we can. But you're never described by exactly Brownian dynamics equation, for instance. That's not a fundamental equation of nature. There's always a level of coarse graining, and that level of coarse graining will break down if the quality of your data improves. If I have very, very short delta t data, then you'll see that inertia will start to come up. Even shorter delta t, you may see even weirder effects, That's such like the speed of sound of the speed of sound of the medium, creating correlations and hydrodynamics correlations, etc., etc. Your level of description should be adapted to the quality of the data and the complexity you want to put into your model. Now, so far, this is perfectly right. We've used these methods at the same level as the ones we simulated. There's, I think, a really nice route to explore that we haven't really tackled yet, which is using this kind of methods to coarse grain.
Yeah.
To do, for instance, stochastic partial differential equation inference based on data that were obtained using agent-based models. Using that experimental data or even simulations, because then you're using this to find an effective model.
Yeah.
Now, one complexity, of course, is that then there's no right model, right? Again, it's going to be harder to find statistical tests to make that tell you, well, you've succeeded completely. But it's a very nice challenge. And now, compatibility between these different levels of description, that's more of a theoretical physics than an inference problem, meaning that lots of people have looked at, for instance, how you get hydrodynamic or active matter continuum descriptions of agent-based systems. And so it would be great to see if doing these exact approaches to the inferred model at the agent-based level, or how it compares to the inferred model at the coarse-grained level. That's a very nice route to explore. And of course, this would have applications in biological physics.
Thank you, amazing.
Is there any other question? Comment?
I'll just tease you. This is the data set that we did not discuss. And that's the one you should ask Joao about. And it's very cool.
All right, so if we don't have any other question, let's... you have one question. No, you can, please. If you want. Sorry, I didn't see your hand.
No, I was just wondering whether the pastors data set is, the paper and the package are basically already published, or whether this is what you mentioned was on the pipeline.
Pastis is still in development. All the data I've showed were produced yesterday. No, this one is a bit older, and it's not exactly the up-to-date version. The stochastic force inference package, the first version is published. Next version is going to come online in the next few weeks, I hope, so that I have time to polish it and work out the small problems that are in there. And that's going to be, I hope, nice to use and user-friendly. Lunchtime?